Hi, this is the next video on points of inflection. So in the first video I talked about the fact that a point of inflection is defined as where a point at which the graph changes from being concave, where the second derivative is less than or equal to 0, to where the graph is being convex, which is where the second derivative is greater than or equal to 0, or vice versa. Okay, so a point of inflection is where that graph changes from being less than to greater than. So we can work out the location of a point of inflection by solving where d2y by dx squared actually equals 0. Okay, now if we want to work out the location, we need to solve that, but then we also need to show that the second derivative has a sign change on either side of that value, okay, or of that point, so that we are showing that the graph changes from concave to convex or vice versa. Okay, in this video I'm just going to do a couple of questions to show you what sorts of things you might get asked in the exam. So the first question, the curve C has equation y equals x cubed minus 2x squared minus 4x plus 5. So for part A, we've got to show that the curve is concave in the interval negative 2 to 0 and convex on the interval 1 to 3. Okay, so for part A, we need to show that it's concave. So where it's concave, that's where the second derivative is less than or equal to 0, and where it's convex, that is where the second derivative is greater than or equal to 0. So the first thing we need to do is get to the point where we've got the second derivative. So if I differentiate it once, I'll get 3x squared minus 4x minus 4. And then if I differentiate it for a second time, I will get 6x minus 4. Okay, in the interval minus 2 to 0, so that's where x is greater than or equal to minus 2, but less than or equal to 0. Okay, well, for one thing, when x equals minus 2, that'll give me minus 12 minus 4, which is minus 16. And when x is 0, that will give me minus 4. So when x is minus 2, I'll get minus 16. When x is 0, I will get minus 4. And this is just a linear expression. So imagine a straight line, y equals 6x minus 4. Then it's going to be, y will be negative for all values in that interval. If it's negative where x is minus 2, and it's also negative where x equals minus 4, then it will be negative for all values in that interval. So I'm going to write that 6x minus 4 is going to be less than or equal to 0 for all values where x is greater than or equal to minus 2, but less than or equal to 0. Therefore, it is concave on the interval negative 2, 0. Okay, now I can do the exact same thought process again. If I now consider where x is greater than or equal to 1, but less than or equal to 3, so we're looking at this interval here now, then again, if I substitute in when x is 1, 6 minus 4 will be 2, and when x is 3, 18 minus 4 will be 14. So if the second derivative is greater than 0 when x is 1, and it's also greater than 0 when x equals 3, because it's linear, then it will be greater than or equal to 0 for all values in that interval. So 6x minus 4 is greater than or equal to 0 for all values in that interval. Therefore, the graph is convex on the interval 1, 3. Okay, part B says, find the coordinates of the points of inflection. So I'm just going to get rid of that. So with the points of inflection, we know, for the points of inflection, we know that d2y by dx squared equals 0. So we need to solve where 6x minus 4 equals 0. So if I solve where 6x minus 4 equals 0, then 6x will equal 4, which means that x is going to be 4 over 6, or 2/3. Okay, now we need to show that when x equals 2/3, that is in fact a point of inflection. Okay, so we need to show that there is a sign change where x is slightly smaller than 2/3 and where x is slightly bigger than 2/3 to show that it's switching from concave to convex. So if I say that's approximately 0.6 or 0.6 recurring, then if I do 0.6, so that's just slightly smaller than that, so that's just to the left of 2/3. If I then substitute 0.6 into 6x minus 4, I will get negative 2/5. If I go slightly to the right of 2/3 and substitute in 0.7, if I substitute 0.7 into 6x minus 4, I will get 1/5. So just to the left of 2/3, d2y by dx squared is negative 2/5, so that is where it's concave. Just to the right of 2/3, where x is 0.7, the second derivative has a value that is positive, so that is convex. So we've shown on either side of that point where x equals 2/3 that the graph is concave and convex, therefore it must be a point of inflection. So we've got a sign change, therefore we have a point of inflection. And the only other thing to do is work out, because it wants the coordinates, is work out the y value. So if we set x equals 2/3 and substitute that into the original function, then 2/3 cubed minus 2 lots of 2/3 squared minus 4 lots of 2/3 plus 5 gives us y equals 47/27. So the point of inflection has coordinates 2/3 and 47/27. Okay, let's look at another question. F of x equals 2x squared natural log x. Show that f has exactly one point of inflection and determine the value of x at this point. Okay, so for the point of inflection, if it's got one point of inflection, or if it's got a point of inflection, that is where d2y by dx squared, or f double dash x, equals 0. Okay, so we're going to have to differentiate this twice. So we have a product of two different functions. So we're going to have to use the product rule for the first derivative. So I'll just switch colour. So if I say u equals 2x squared and v equals natural log x, du by dx will be 4x and dv by dx will be 1 over x. So the first derivative f dash will be v du dx, so 4x log x, plus u dv dx, so 2x squared times 1 over x. One of the x's cancel, and we're left with 2x. Okay, now this is another product, so we're going to have to do the product rule again for the 4x natural log x. So if I say u equals 4x and v equals natural log x, du by dx is 4, dv by dx is 1 over x. So now I can do the second derivative. So f double dash x is v du dx, so 4 natural log x, plus u dv dx. Now again, the x is going to cancel with the x, so we're just going to be left with the 4. But we've also need to differentiate the 2x, so the derivative of 2x is 2. So f double dash x will be 4 natural log x plus 6. Okay, now we know that 4 natural log x plus 6 is related to the graph of natural log x. Okay, there is only one point of intersection. It's only going to cross the x-axis once. Therefore, if we try and solve 4 log x plus 6 equal to 0, there will only be one root. Okay, so 1 point of inflection. Okay, which we can work out if we solve that. Miss my x off. So if I say 4 log x equals minus 6, log x is negative, so it's negative 6 over 4 or negative 3 over 2. And then to undo this, I need to get it out of log form and get it into exponential form. So x will be e to the minus 3 over 2. Okay, now we need to check either side to confirm that this is a point of inflection. So if I stick that in my calculator, I can see that that is equal to 0.0223, etc. So if I work out the second derivative, where x is 0.022 and where f is 224. So just going slightly either side of that. So I'm going from, instead of 0.0223, I'm going 0.0222 and 0.0224. One is just to the left, one is just to the right. If I pop those into my second derivative, I will get negative 0.02, that is concave, and I will get 0.02, that is convex. So that's just substituting those two numbers into the 4 log x plus 6. Okay, here we've got a sign change, which confirms that there is a point of inflection. Okay, so we've shown that there's one root because there will only be one point of intersection. We've worked out the x value because that's all we needed. And then we've confirmed that there is a point of inflection by looking to see if it's concave and convex on either side. Okay, let's have a look at one more. Slightly different. So for each point on the graph, state whether the first derivative is positive, negative or 0, and the second derivative is positive, negative, or 0. So I want you to pause the video now and just have a little think about what you know about the gradient at each point. So f dash x is the gradient, positive, negative, or 0. And then what you know about the second derivative. Is it concave, in which case it's negative? Is it convex, in which case it's positive? Or is it 0, where there is a point of inflection? Now remember, it doesn't have to be a stationary point of inflection. F double dash x will be 0, where it changes from concave to convex. Okay, so let's just have a little look. So if I just put A, B, C, D. Okay, so the gradients, I should imagine, were easier to think about. So the gradient at A, we can see if we imagine a tangent to A, that tangent would have a negative gradient. So the value of the gradient function at A would be negative, therefore less than 0. At B, at B there is a turning point, so the value of the gradient function there would be equal to 0. At C, if we imagine a tangent to the curve at C, that would have a positive gradient, so therefore the gradient function has a value that is greater than 0. And at D, well, if we imagine a tangent to that, that would be horizontal, so it would be parallel to the x-axis. That would be equal to 0. Now if we think about the second derivative for each one. So now we're thinking about whether the graph is concave or convex. So at A, okay, at A, that is going to be a convex part of the graph. So all along here, if I just go over it, all along here, probably until we get to about here, the graph is going to be convex. So therefore that is going to be greater than 0. Okay, at C, just change colour. At C, all along here, the graph is going to be concave. So that is less than 0. At B, sorry, made a mistake there. So that is C. At B, it's still part of where the graph is convex. So that is greater than 0. At D, well, at D, we have a point of inflection. So the graph, if you think of y equals x cubed, so that is going to be where it is equal to 0. And that is a point of inflection. It's also, because that is equal to 0, a stationary point of inflection. Okay, so it's stationary and a point of inflection. It's likely that the other point of inflection is about there. So where the graph is changing from convex to concave, there will be a non-stationary point of inflection, roughly there. So it's worth, in future, just as you sort of run your finger along a curve, it's worth thinking about, is that graph concave or convex, and where is that point of inflection? Okay, that's the end of that video. It's worth now probably going and having a look at some practice questions to see if you can work out where the points of inflections are and how to show that it's a point of inflection. Okay, thank you.